So, good morning. Let's get started. Thank you. Today, I want to talk about building a very interesting number system. I want to build a really interesting number system. And the way we're going to build our number system is we're going to start from the familiar real numbers. Are we all familiar with what real numbers are? Real numbers? Yeah. So, by convention, can everybody see what I'm writing here? Yeah. Are we good? Yeah. I'm going to write the set of all real numbers as this R with the funny back here. Set of all real numbers. And real numbers have a lot of interesting properties that's going to let us do some funny things with it and build a very interesting system. And the way we build systems, the way we build countries is sometimes by democracy. And today we're going to use democracy to show how we can make a number that behaves like real numbers, but have some extra nice perks that allow us to do things we normally cannot do with real numbers. Okay, so for democracy, what's the most important thing in democracy? I think it's voting. And to do voting, we need a lot of voters. So we can't do that with a number. So what I'm going to do here is we are going to work with infinite lists or infinite tuples, infinite order sets. What I'm basically talking about is like just a list of a lot of numbers, 3, 4, 5, 17, 17, and so on. These can be just anything as long as they are real numbers. They can be negative, they can be fractional, they can be irrational. So here are some examples: 0, 0, 0, and so on, where every slot is filled with 0, 3.1, 3.14, 3.141, and so on. They don't necessarily have to follow any rules. They can just be a list of real numbers. But importantly, they have to be infinite. We're not going to deal with finite lists. They have to be infinite. Okay, just a notational thing. I'm going to write this as R to the power of infinity. This is just like a notational thing. So how we write R power 2 to indicate the Cartesian product between two real numbers. This is just going to mean the ordered pair, the set of like all ordered pairs where each element is a real number. Just a notational thing. So in the end, I'm going to write R power infinity to denote this new set we have where each element is not a real number, but an infinite list of real numbers. Okay. So ultimate goal is like we're going to show how R infinity, I'm just going to call them new reals, the new reals. We're going to see why I call them new reals in the future. We want to see how new reals behave like ordinary real numbers we used to know, plus with some very interesting objects in them that we can't like find in other number systems. Okay. So I mentioned voting, and here is how voting is going to work in the new reals. So when I'm saying a vote, I'm going to put a question to the vote. I'm going to ask a question about some infinite lists. And the voters are going to vote yes or no. And whoever has more votes wins. So let's try to look at claim 2 right here, which is to say, is the new real 17, 17, 17, and so on, where every slot is 17, equal to 0, 17, 17, 17, and so on, where every slot after the first one is equal to 17. What do you think about this question? So it's like how voting works is like there is a voter responsible for the nth slot. So there's a voter responsible for the second slot of everything. There is a voter responsible for the third slot of everything and for every natural number. So what this is like voter n only gets to look at the nth element of each, only gets to look at that one. So in 17, 17, 17 and 0, 17, 17, 17, I'll just call this alpha, I'll just call this beta. So what does voter 1 think about this question? Is alpha equal to beta from voter 1's perspective? Anyone? Tego's shaking his head. No, because voter 1 only gets to look at the first slot of each, which 17 does not equal 0. Therefore, voter 1 is going to vote no. What about voter 2? Thank you. Yeah, voter 2 is going to vote yes. What about every other voter after 2? They're all going to vote yes. So let's tally the votes. We're going to get no, yes, yes, yes. Oh, that's a lot of yeses, which is to say there are only a finite number of no's and an infinite number of yeses. So I think the vote goes to yes. Therefore, alpha equals beta. They are the same number according to our voting system. Do you all get how this voting system works? Okay. Feel free just to just stop me whenever you have questions or something is unclear. Okay. I have a lot of exercises for you. Okay. Number 1, let's try this. It's 1, 2, 2, 2, 2 equal to 17, 17, 2, 2, 2, where every slot after the third one is equal to 2. Can somebody here give me an answer? Or everyone in this Zoom? Shout it out.
The first and second voter will say no, and the rest
Sorry?
of the
Yes.
first and second voter will say no, and the rest of
No,
the
no.
vote will say yes.
Yes. So which one wins?
So the majority is yes, so I guess it is equal.
For the first one?
I mean, like in general.
Oh, I hear you discussing measure. That's an interesting notion. We're going to talk about some more edge cases in the next few slides, but for the time being, the answer I was looking for in number 1 is only 2 votes turn out to be no's, and the rest, which are an infinite number of them, turn out to be a yes. So these 2 indeed will be the equal numbers for the first one. Does this make sense to everyone? Same thing we did in the previous slide. Yeah, I'll get back to you on the size of sets and how we're gonna determine votes. Okay, number 2 is 17, 1, 1, 1 less than 0, 17, 17, 17. Is this inequality going to hold true? I see a lot of nods in this room, so I'm gonna say yes. Only a finite number of people disagree. Everything else who looks at their particular number is going to say yes. Infinity beats finitely many voters. Number 3 is a bit difficult because we have an operation going on. Is 17, 1, 1, 1 plus 17, 2, 2, 2 equal to 3, 3, 3, 3, 3? It's a bit difficult because we have a plus here. But again, the second voter, for example, only gets to look at the second slot of everything. And from their perspective, 1 plus 2 equals 3. Therefore, infinite number of people agree. Only finally many people disagree. So this is also true. So wonderful. We can now add real numbers and see what their sum is equal to. That's huge progress. Okay. The next 2 are, I think, some of the most important results in this slide. And this might take a while. So first one, for all real numbers in R, we're going to build an infinite list where every slot is equal to R. So R, comma, R, comma, R, and so on. Is this number for all R less than 1, 2, 3, 4, 5, a progression that goes on and on and on? This number is so important. I'm going to call this omega. Omega equals 1, 2, 3, and so on. What do we think about this question? For all real numbers, is this less than this omega? I see a few nods. Can somebody give me a brief reason why? Yeah.
It is, yes, it is less than the omega because,
Yeah.
for example, if R it has the same values and it just continues infinitely. So
Yeah.
when it reached the same number as the R in the omega, there will be infinite bigger number than afterwards. So
exactly. Thank you. Yeah. So all voters from 1 to the floor of R, which is a finite number, is going to disagree. Exactly what you said. Everyone else, which is an infinite number of people, are going to disagree. Is going to say it's less than that. So yes, this holds true. So I think this is very interesting because we have a number we call omega that's bigger than all real numbers, so to speak, where every slot is equal to that particular number. No, the next one is highly similar, except we have reciprocals 1/2, 1/3, 1/4, and so on. This number is like even more important. We're gonna call it epsilon. Epsilon equals reciprocals. For all positive real numbers, is this everything where every slot equals to r greater than epsilon? I mean, sure, it's the same reasoning above, just put differently. Okay. Let's try to put omega and epsilon in our minds. It's going to prove very important in the last few slides of this presentation. A final question. There are some harder ones here. So we can also ask more general questions about alpha and beta, where is the commutative property of an infinite list going to hold under addition? You have to think a bit carefully, and to actually do this precisely, we need to use a set theory definition of voting systems that we're going to discuss in a minute. Okay. But we can kind of see where this is going to go. We can kind of see why this is going to be true, because commutative property and like order of operations and like addition, subtraction, multiplication, division, they all work as expected, like with respect to each slot. So this kind of gives us an intuition why it should also work for the new real numbers. A final exercise before we move on. I'm so out of time. That is it true that omega is 1/epsilon? What do you think? Omega and epsilon, reminder right here. Is omega equal to 1/epsilon? This is a quick puzzle. Can we get a show of hands who think they're the same thing? They are the same thing? Oh, that's like not as many people. Yeah, they are the same thing. Same thing we did. Just every voter agrees it's a reciprocal. Epsilon times omega is 1. Omega is 1/epsilon, and so on. Pretty simple. Let me just finish off with the last one. This was a long slide. Is omega a natural number? Is omega a natural number? Weird question. Is omega a natural number? What's voter 1 going to say? It is a natural number. 1 is a natural number the last time I checked. What is 2 going to say? Yeah, 3. And so on. So omega is a natural number. Omega is a natural number, no doubt. Consensus, everybody votes yes. And that's great. Let's look at we have to face the unfortunate truth now, which is to say, if we have an infinite number of voters, that if an infinite number of people vote yes, and an infinite number of people vote no, what are we going to do? So is 17, 17, and so on, everything equal to 17, equal to 17, 0, 17, 0, 17, 0, and so on, where 17 and 0 are alternating. Difficult indeed. Do we all see why we get a problem here? All the even number voters, sorry, all the odd number voters are going to say yes. All the even number voters are going to say no. So here we have like voters 1, 3, 5, 7, and so on are going to vote yes. Voters 2, 4, 6, 8, and so on are going to vote no. Which one wins? Which one is bigger? So I think someone also mentioned at some point, if you learn about the size of infinite sets, and like if there's a bijective function between these two sets, they are considered to have the same size, even if they are infinite, or even if like they're subsets of each other. That's a result that I'm not gonna go into now because it's like not relevant. But because there's a bijection between them, these two sets actually have the same size for intuitive reasons as well. So which one is going to win? Do we have a tie vote? Or is this vote in like a quantum state where it's like half true and half false at the same time and we have to observe it? So the answer here is like, we don't really know, but God is going to tell us the answer. That is literally what we are going to do. We're going to ask God what the answer is. We're going to consult the oracle. You know, the oracle at like the Greek temples. We're going to ask God whether this is like true or false. Okay, so we're going to redefine what it means to win a vote. Do y'all know what a coalition means? Coalition just means like a group of people coming together for a cause. So a statement about infinite list is true if the winning coalition of voters vote true. What is a winning coalition? Winning coalition is like just a set of voters who are going to win if they vote for the same cause. I repeated what I said. Let me go back to an example that's right here. We collect the number of voters who respond yes to this question and the number of voters who say no to this question. And we get a set of voters who agree and a set of voters who say no. Which one is going to win? The answer is whoever is a winning coalition. Whichever set is a winning coalition, they're going to win the vote. And here I have a set theory. Okay, I'm gonna write a fancy W to denote the oracle. This is a set of sets. W lists out all the sets of voters who can win a vote if they vote for the same cause. And the important thing is we don't really know what fancy W, we don't really know what W is. We're just gonna know that it's going to exist. I know I'm being very, very abstract right now. It's like we can build many different worlds in which in some worlds 1, 3, all the odd number slots are going to be superior to the even number slots and they're going to win the vote if they vote for the same cause in some particular world. And in other worlds, depending on our other choice of oracles, we can have the even number voters win the vote. So essentially W is like our choice of God. We can choose like any god we want to give us like whatever answer, and the god just has to be like a sane person and satisfy a certain set of rules. So can a finite number of voters win a vote? I mean, according to our intuition, like, no, that'll be really bad because there will be less people voting and they're still going to win. So the set of voters, if the set of voters is finite, it cannot win. It cannot be a winning coalition. Number one is really important. This is to say, so the reason why 0, 17, 17, and so on was equal to 17, 17, and so on, the reason why they were the same numbers was exactly because so here the people who vote no are going to be only one. The voters who are going to vote yes are everything after that. The people who voted yes won this vote precisely because this set has to be a winning coalition, as in it has to be part of Omega. This is the reason why they won this vote. And for this, it's like crystal clear because the other set is finite. Therefore, this one always has to win because it has more of them. But so this is going to hold true no matter our choice of gods, because even gods have to follow some rules. But for cases like this, we can choose either one. Our god can prefer either one, and it's still going to be a perfectly fine system. So the second set of rules, this is like also really important. If A is a winning coalition, the complement of A cannot be a winning coalition. What this essentially says is like no coalitions who like vote for the different things can win at the same time. A vote is unambiguously either true or false. Okay, nothing in between. This is again just like a rule our god has to follow depending on like what type of god we choose. The third and the fourth one can be a bit tricky. I'm just gonna go over them really quick. It's like not crucial that you get them right away. If A is a winning coalition, if the set of voters A, they are going to win under our choice of God, a set that includes all of it also has to win. What this is saying is like we can't suddenly have more voters changing sides to an already winning vote and like lose somehow. If something is winning, if people support it even more, they still have to win. And number 4 is also interesting. If A and B are winning coalitions, their intersection also has to be a winning coalition. Number 3 and 4. I think they're a bit tricky to get right away what they mean, but if you try out with a few examples, it's just a set of rules to make sure our God doesn't make really, really insane decisions. But otherwise, it's just really up to God. Like, we don't really know whether this is yes or no. We don't really know if they're equal or not. We just know that it's either one and exactly one of them. For when something is finite, we know for sure because even God has to follow some rules. This one, it's up to God. We can have like perfectly many versions of God that tell us very different things. We're still going to be fine. I know there was a lot of abstract things going on. The good news is like you don't necessarily have to grasp all of this right away. I took this whole thing over like a week, and it definitely took me like a few days to settle this, a few days for this to settle in me. So yeah, it's completely fine if this doesn't feel too intuitive right away. It's not going to be crucial for the slides that are to come. I'm just here to show you that even cases like this, we're unambiguously going to have equal or not equal. Exactly one of them. We don't really know. We don't really care. Do you have a question?
If it's like for every 4n plus 1,
yeah,
then like it's yes. For everyone else, it's no. So if like set A is like every 4n plus 1, then a winning thing. But if there's a thing that includes A, like 4n plus 1, 4n plus 2, and 4n plus 3, doesn't that mean that B actually loses?
So we have a set 1, 5, 9, and so on. This one. And so this one's, you said this one is going to win? If this is a winning coalition, then what's the latter point?
Let's say that like in the like in like the what was it like they said? So everyone in
Oracle,
plus 1 says yes.
Yeah.
Everyone else says no. So
everyone else says no. Okay.
So if like the set on the top is A, and A is a part of B, which is basically 4n plus 1, 4n plus 2, and 4n plus 3.
A is a part of B. Yeah.
Like B is basically 4n plus 1, 2, and 3.
4n plus 1, 2, and 3.
So doesn't that like kind of change the outcome of the?
Oh. If this is a winning coalition, I think what this tells us is that B also has to be a winning coalition, but this should be under the same omega. And if you said this was a winning coalition, if the people here vote yes for a cause, even though it feels like a complement should have more people in them. So what I'm saying, I think where your question points to is like the converse of number 3 doesn't really hold true. It's not like, yeah. The converse of number 3 doesn't hold true. You can have less voters in something and like still get a yes. That's going to be fine. What we do know is that B has to be winning under our choice of God, under our choice of W. B has to win in this case, but it's not true that this is going to change the outcome, even though it has like more people in them. Yeah, I hope that answers your question. Okay. Next one, we have seen a lot of cases. I'm so behind time. I will speed up. We have seen a lot of cases where all the slots are equal to one particular number, like R, comma R, comma R, comma R. Right now, I'm going to make a really, really bold move and just call this R. I'm just gonna set equal. This is like just a notational thing. So 17, what is 17 going to mean? 17 is going to mean 17, 17, 17, and so on. But is this the only thing that's 17? Is this the only thing that is 17? No, no, no. What about this? This is also 17. They're the same number. What about 17, 0, 17, 0, 17, 0? Is this also going to be equal to 17? We don't really know. Depends on our God. But it may or may not be. But what I'm saying here is like 17 is like an equivalence class. It's like there's a lot of things that are equal to 17. We're just gonna call it 17. And if it's equal to just a real number we know, we're just gonna call R, this new real number, a standard real number. Standard real. Please let that sink in. We're going to call it a standard real number. Is this clear to everyone? Yeah, there are a lot of numbers that are there are a lot of real numbers that are standard reals. There are a lot there are a lot of them that are not standard. And definition 5 is crucial because it's the most interesting thing in the new real number system. What are infinitesimals? Has anyone heard of the term infinitesimal before? Yeah, it's like infinitesimal is like infinity is like something that's so far from zero. It's like not even a number. Infinitesimal is something that's so close to zero. It's like not even a number. It's like 1 over infinity, so to speak. So this is ambiguous in the real number system, and we work with like limits. If you took calculus, you'll know what I mean. Infinitesimal here is very straightforward. Delta, which is a new real, is infinitesimal if and only if for all positive reals, the absolute value of delta is less than r. What about epsilon? What about 1, 1 over 2, 1 over 3, and so on? Is this an infinitesimal? Is epsilon an infinitesimal number? Yeah, I think we all answered yes when we asked this question. Is this value greater than this? It's true because only finitely many ones will say, yeah. And whether something's an infinitesimal or not, just to note, can also depend on our God. Depending on what our God considers a winning coalition, we can have different sets of infinitesimals. But in any case, epsilon is always an infinitesimal, for example, because it's closer to zero than all real numbers. All positive real numbers. Okay. And are infinitesimals always positive? No. Because minus epsilon is also an infinitesimal. That's why we have a delta here. Is 0 an infinitesimal? Is 0 infinitesimal? According to our definition, yes. It's really up to philosophy and like debate and like a lot of convention whether 0 is an infinitesimal or not. We're just gonna think of 0 as infinitesimal because it's going to be convenient in the future. So we're gonna write the set of all infinitesimals as I. I know this looks nothing like I, but trust me, it is. This fancy I is going to be the set of all infinitesimals. I will be very important. I'll use this frequently. And we have a squiggly equal sign, which we usually don't use with a precise mathematical meaning. But today, like it's your lucky day, we are going to. Alpha is approximately going to equal beta, squiggly equal, if they differ by an infinitesimal amount. So alpha minus beta, if like their difference is part of I, if their difference is infinitesimal. So quick exercise is epsilon squiggly equals 0. Does epsilon squiggly equal 0? What do we think? I think yes. Is 17 approximately equals 17 plus epsilon? What do we think? Yeah? Okay. I'm glad we're on board. Theorem 6. This is huge. Let's try to understand what this monstrosity is saying to us. If alpha is bound by some standard real number, what do I mean by bound by some standard real number? What I'm saying here is alpha is not infinite. The reason I will say alpha is not infinite is like we have to be very careful about what it means for a set to be infinite here. That's definitely not in the scope of this lecture. But what this means is like alpha shouldn't be something like omega where it offshoots everything and like goes off the scale. Alpha should be something we know that it's like that we know to be less than a standard real number. Something we know to be less than a standard real number, something we know. All right. If this doesn't hold true, alpha is like the same way we define infinitesimals. Alpha is a type of infinity. So we're not going to talk about that. So for every bounded standard real number alpha, it's going to approximately equal, it's going to be infinitesimally close to some standard real, something that's standard. Alpha does not have to be standard. It just has to be bound by a standard number. But in any case, it's still going to be infinitesimally close to some standard real y. Does this make sense to everyone? Somewhat, maybe. It's like if we have a set, if we have like a, let's have like a weird infinite list and say, fortunately, it's going to be bound by something like, oh, fortunately, even if we go like too far, the absolute value of alpha, it will be less than 17. Oh, this is very nice. What this tells us is like alpha is somehow going to converge. It's going to be approximately equal to some standard real number we know. That's important because standard reals is something we really know how to deal with. This theorem is, the proof of this theorem is, it's not that hard, but it's going to need something called, it's going to rely on something called the completeness axiom, which some of you might be familiar with. I don't think I'll go too much into this for this lecture. If someone's curious about the proof, just let me know. It's really not that hard and very interesting to go through. I mean, if I have time left at the end of the lecture, maybe I'll come back to this. And fortunately, what we have next is the last slide, 8 out of 8 right here. However, we have a lot of like tasting to do. So let's look at like what we achieved so far with our infill lists. Like, why did I do this in the first place? Because without like these implications, this is like absolutely useless. We built something that behaves kind of like, okay, I shouldn't use this line. This has precise mathematical meaning. Kinda, I'll use like kinda equal. This is kinda equal to like R. It behaves in similar ways. We can add them, we can compare their sizes, we can see if they're equal or not. And even here, but what's present in our infinity that is not in our standard reals? What's in our new reals that are not in our normal reals? Can somebody just like list out some things we did? Something more we have here? Oh God, yeah. That's beautiful. Yeah. So it's like we get many, many different ways to add and subtract and see if which things are equal depending on our choice of God here. Yeah. R is like atheistic. Anything else? Anything more we have? Do the real numbers have infinitesimals? I'm gonna say no, because every real number, it's like if you have two real numbers, there's something in between them. We can't have like a number where nothing is between that and 0. We can have something that's like infinitesimally really close to 0. That's like not possible. So R has no infinitesimals. I can just write infinitesimals for something we have in the new reals. Yeah. Sorry? I thought somebody spoke here. Maybe not. Do we have infinity in R? Like, no, guys, no. That's like infinity is not a number. Do we have infinity, something that's greater than all standard real numbers in our system? In fact, we have a lot of them, like 1, 2, 3, and so on. Omega is one. 1, 2, 4, 8, and so on. Yeah, we just have a lot of them. 9, 17, 17. And something that's like everything that offshoots, that goes off the edge, they're all going to be infinities. And all their reciprocals are going to be different types of infinitesimals. So there are like so many of them, we have to collect them in a set, something like I. So we have a lot of infinitesimals. We have a lot of infinities. And both the fact that we have infinitesimals and we have infinities are going to produce some really unexpected results. Let's look at this. Okay, let's look at continuity. Are we all familiar with what continuity means? I don't really expect you to be, because it's just a calculus thing. Have you heard of continuity or what it is? Continuity is like, A function is, there are better definitions. A function is continuous if it doesn't have jumps like this, if the value doesn't jump at a particular point. This is like not continuous. Or something like this, if like something offshoots to infinity and like goes down to infinity, there's nothing that's connecting them here, so they're not continuous. A way we can look at continuity using infinitesimals is like, if at a particular point A, if we deviate from A, if we move back and forth from A by an infinitesimal amount, the difference in function value should also be infinitesimal. But is this the case here? Say this is 17 and say this is 1. From A, we're going to move an infinitesimal positive amount to alpha, which is A plus epsilon, maybe. Is the function value, what's the function value? It is 17, even if we moved by a tiny, tiny amount. The reason this is true is because infinitesimals are unambiguously positive or negative. They unambiguously have signs. So, yeah. If we plug in like A plus epsilon, where epsilon is positive, it's going to give us 17. If we plug in A, what do we get? This is really bad. I'm just going to, this is not going to be a value here. And yeah. What's the value we get for FA? 1, yeah. But this is like a huge jump. If we moved really, really small in the X portion, we should also get a really, really small change in the Y direction. So according to our definition, this cannot be continuous at point A. And this is another way we can look at continuity. And if you are familiar with something called limits of a function, you can also see why taking the limit at a particular point is just equal to plugging in A plus an infinitesimal amount. And a limit is going to exist if this value is equal to the same thing no matter our choice of infinitesimals for any choice of epsilon in the infinitesimals. I'm really sorry if calculus is not familiar to you. We have a more interesting result here. Can we find the slope of the line tangent to y equals x squared at the point x, at the point 1, 1? What is going to be the line that's tangent here? What is going to be the slope of this line? Ooh, we're gonna just use our slope formula. We're gonna compare 1 and something at 1 plus epsilon. Because I think a tangent line is like just a secant line that goes through 2 points, except those 2 points are like really, really close. And this just gives us our slope formula if we know how to plug in to the function value. So we have the function value difference above, delta y. We have the function. We have the x value difference below. What's this one going to give us? Remember, you can definitely divide by epsilon on both sides. Epsilon is a well-defined number. You can definitely divide things here. In the above, if we do some algebra, it's going to give us this, which is going to give us, trust me, you can divide by epsilon. This is not wrong. This is completely fine. 2 plus epsilon. And I think epsilon is infinitesimally close to 0. So what is this infinitesimally close to? Oh, 2. So I think the slope of this is going to be 2. And if, again, you had calculus before, you can see that this is a redefinition of the derivative, only nicer and without the involvement of limits whatsoever. So this is a neat technique. The last thing I'm going to do in my lecture today is going to be, there are some theorems known as the intermediate value theorem and the extreme value theorem. They're all calculus analysis adjacent theorems. But if you want to formally prove this without our really cool new real number system, I think you need like months of a college course in real analysis. We're not going to do that. I'm not going to do a full proof here. The sketch of the proof is like you can divide. Okay, who remembers when I said omega 1, 2, 3, 4, and so on? Is this a natural number? Yeah, by consensus. It's like as a natural number as it can be. Okay, if omega is a natural number, okay, if we have the interval a to 0, the open interval a to 0, or it can be closed, doesn't really matter. Oh no, that's unfortunate. can we chop this interval up into 3 pieces? Yeah, I think we can do something like this, where we have 3 pieces right here. What's the length of each of these intervals? B minus A, the length of the total one over 3. Don't think about measure. This is unambiguous. We can chop this interval up into 3 of them. Okay. Can we chop this up into 17 of them? Sure, why not? Can we chop this interval up into omega many of them? This sounds so wrong, but no. Omega is a natural number. What are going to be the starting points of each of these? They are going to be an arithmetic sequence if like all the intervals have equal length. So the starting points of these were, first one is we just call it A0, A1, and so on, all the way up to, we're going to go up to A omega right here. Okay. AK is just going to be A0, well, I'll just call this A, plus the length of the interval, which will be B minus A divided by omega times K. It's going to A0 is going to be A omega is precisely going to stop at B. So can we chop out this interval into omega many pieces? No problem. It's completely fine to do that. Okay, then what's the length of each of these intervals? B minus A over omega, which we can rewrite as B minus A epsilon. And using this, what we can do is like we can chop up this interval into omega many pieces, and that's going to give us and now what we have is a way to talk about functions over an interval with only finitely many points. So this kind of turns continuous functions into sequences and like finite sets that we can analyze. I'm not gonna go too deep into that, but what this also allows us to do is to chop up an interval into infinitely many pieces that have the same length. This is also used for integration, and it's going to be defined the exact way you'd imagine, but without the difficulties of normal calculus. Or maybe this is more difficult, I'm not too sure, but I think that's all I have for today. Thank you very much.